the additional variability that wind brings to the system does have a cost. It means that you're going to be moving or ramping some of your other conventional generators more than you would before. Some of those units may be going to a less efficient point on their heat rate curves, therefore you're burning more fuel per megawatt hour than you otherwise would be burning. There also is a cost of uncertainty, and I'll talk more about this in a few minutes, but wind can be predicted, but it can't be predicted as accurately as we can predict the load. We can't predict load perfectly accurately either, but wind brings per unit a larger level of uncertainty to the system than load does on a per unit basis. And that uncertainty also has a cost. So the table that you see here shows the result of a number of wind integration studies that have been done around the U.S. That have attempted to try to calculate the cost of integrating the wind. So the cost that you see here does not include the fuel benefits from adding wind to the system. It does not include the total cost of running the system. It's essentially looking at the production cost of running the system and the cost increment that wind brings to the system. So, for example, if you take a look, there are a couple of high penetration studies that have outlined. Let's jump to the next to the last one at the bottom. December 2006, the Minnesota 20% study, which is the data that we've been looking at. The integration cost was roughly $4.41. That was an average over 3 years, taking a look at the 25% penetration rate. So what that means is that the increase in variability and the increase in uncertainty that wind brings to the Minnesota system has a cost, and that cost is around $4.50 a megawatt hour of wind. So this is $4.50 per megawatt hour of wind. It's not $4.50 per megawatt hour of load. And you can see that there are a number of other studies. The costs range, and $5 seems to be about the high end for the penetrations that have been looked at so far in the United States. Let's go to the next slide, please. Can wind power start and stop suddenly? You know, the funny thing about wind, we all have our own personal experience with it, and walking around at less than 2 meters off the ground, as I do, the wind is acting very differently down where I live as opposed to where the wind turbine lives, which is up at about 100 meters off the ground, maybe 80 meters, depending upon the wind turbine technology, how old it is, and so forth. But you get more wind turbines spread over a large wind plant, and then multiple wind plants, as it is the case in Texas, and it was the case in Texas a couple of years ago when this particular event happened. You tend to see a lot more smoothing. Now, this picture is a little hard to see. This was a fairly well-publicized dust storm, and you can see the dust in the graph, in the picture down in the lower center, lower right-hand side of the picture. This is actually a satellite image taken from space at about the time this storm blew through Texas. Wind turbines like to protect themselves, and so when the wind speed hits a certain critical level, the wind turbine will cut off. And that the wind turbine can cut itself off pretty quickly. But in this particular event, we had this large storm moving through that did cause lots of wind turbines to shut off because of the extremely high wind. Over the large footprint where all these wind turbines were located, that event essentially took 2 hours to unfold. And you can see sort of the high points of the graph here where the wind was generating at around 2,000 megawatts and dropped off to just over 500 megawatts in about a 2-hour period. And that's clearly something that the system operator would have some concern over, but oftentimes folks think, well, you know, that those wind turbines could cut out immediately, and so I could be without 2,000 megawatts in a second or even less. And all the operating experience that we have with wind plants around the country demonstrate that just doesn't happen. So can it start and stop suddenly? Well, locally for a given turbine, yes, it can. But the larger footprint that you have and the more wind turbines that you have, the more relative smoothing you're going to get. And a year after this particular event, there was another similar event in Texas, and I'll talk briefly about that a little bit later on as well. Going to the next slide, what about predicting the wind? Can we predict it? We can. We would like to be able to predict it more accurately than we can today. But wind forecasts are really derived from weather forecasts, and the graphic that you see here is a simulation of the Northeast. This is essentially a graphic simulation that shows where these wind forecasts are coming from. The wind forecaster will typically run a large-scale numerical weather prediction model. These models are essentially three-dimensional models of the atmosphere. They can be run on any scale geographically that you want, but obviously if you want a wind forecast, you're going to run it over the appropriate scale. For example, if you wanted a forecast for the state of Minnesota, you'd run the weather model not only over Minnesota, but you'd pick up the Dakotas, maybe part of Canada, part of Nebraska and Iowa, so that you're covering the geographic footprint that you need that has the relevant weather that may be coming your way. There are a number of firms in the United States that do wind forecasting. This particular graphic was provided by WindLogix. AWS TrueWind up in the Northeast is also a good firm doing forecasting. 3Tira out on the West Coast also does wind forecasting. We can go on to the next slide. You can get sort of an idea of the overall forecast accuracy. And this depends upon where you are. The geography in the U.S. is pretty distinct in different parts of the country, and the forecasting can be more challenging in some locations than in others. But if you see the table here, the next day hourly wind power forecast, typically you get a 10 to 14% mean absolute error as a percentage of rated capacity. The next day total energy forecast, usually within about 20% of the actual energy delivery, and the next 2 to 3 hour power schedule, typically 5 to 7% of the rated capacity of the wind plant. There's some other really important issues with respect to forecasting, one of which is, regardless of the accuracy of the forecast, partial knowledge is better than no knowledge at all. And the other, I call this a BFO, brilliant flash of the obvious. The forecast isn't going to do any good unless you put it in the hands of the system operator. And we think here at the lab that one of the key things that needs to be done is that you want as good of a forecast as you can get, but you also want a forecast that meets the need of the system operator and a forecast that you can deliver in a timely manner to the system operator so that the system can be run in a way that makes some sense. We are seeing more interest in forecasts of potentially large ramp events like the one that I showed you a few minutes ago from Texas. The other thing is that as the variability of wind is damped over larger geographic footprints, so are the forecast errors. And according to WindLogix, a recent presentation, I guess about a year ago, the geographic dispersion can reduce forecast errors anywhere from 30 to 50%. And what that means is you may be a little bit high in the forecast in one region, a little bit low in another, and they may, to some extent at least, net out. That may not be terribly helpful on a system that has multiple balancing areas in which these forecasts are spread over, but on the other hand, with a large footprint, you may in fact be able to have some gains as a result of this type of forecast smoothing. Next slide, please. This next slide shows us what actually happened this past year in Texas, about 1 year ago in Texas. And without going through all the details, ERCOT was actually testing a new forecast, wind forecast, and it was in the room right next to the control room operators. And the forecast itself is given by the sort of the light green stair steps that you see in the lower part of the graph, and the yellow trace represents the actual wind. And so take a look at this. The forecast did a pretty good job of estimating the hourly wind energy. The red stair steps that you see up at the top were actually, was a forecast that was developed in the control room that basically said, well, here's what the wind did yesterday. We're going to assume it does the same thing tomorrow. And so the point is that a good forecast is great, but you want to make sure that you get it in the hands of the operator. ERCOT was in testing mode, which makes a lot of sense, but they did accelerate the movement of the forecast into the control room. Next slide, please.